All right, what's up, guys? This is 2007 Form B number 5. This is the slope field question on this test. You're given a derivative, and you're given part of a coordinate plane with dots on it, and asked to draw your slopes in there. I trust you can do that by now, so there it is. Okay, the second one says to find the second derivative in terms of x and y. Okay, and remember, with implicit, right, your first derivative is always inside of your second derivative. So fine, all right, so I'm going to derive this guy. 1/2 x derives to 1/2, y derives to y prime, that puts me to here. And then I replace y prime with what y prime is, right? dy dx and y prime mean the same thing. So you're just replacing y prime with that foolishness and simplifying, and that puts you to here. So that's the first part of B. In the second part of B, it says to describe the region of the xy plane in which all solution curves to the differential are concave up. Well, concave up means that the second derivative is going to have to be positive. So I'm just saying, all right, well, the second derivative has to be greater than 0 if that's true. And then it just like kind of jumped out at me that you got a y, you got an mx, and you got a b all up in here. So I just got y by itself, and it's like, all right, so anytime that y is greater than negative 1/2 x plus 1/2, it's concave up. Part C, let y equal f of x be the particular solution to the differential equation. Initial condition f of 0 is equal to 1. Does f have a relative min, max, or neither at x equals 0 and justify? Okay, so there's two ways to figure out mins, maxes. You can do the number line analysis, or you can do the second derivative test. And we just found the second derivative, so that seems like a really good choice. All right, so I'm just simply plugging 0 and 1 into my second derivative. Out pops 1/2, which is positive. And remember, if you have a positive concavity, you have a low point. So that's going to be a minimum. And then the hard part. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay, something to point out. So if this is a solution to that guy right there, that means when I integrate this, I should be able to get y equals mx plus b out. And inversely, if I derive this, I should get dy dx out. So then it just comes to playing with variables. I would never expect you to get this right the first time by yourself. So what I'm going to do is I'm going to go ahead and derive this. So if I derive this dy dx, I'm just going to be left with an m, right? So like that's in purple right there. Now, I kind of just from doing these questions knew I was probably going to need to have some kind of an x to equate the variables. So I just kind of put this 0x off to the side right here to be used later. So this is like one version of dy dx. Now, right here, dy dx equals that stuff. See, there's a y in there. Okay, so I can write dy dx a little different also. I could say dy dx equal to 1/2 x plus, well, substituting in mx plus b minus 1. Okay, I combined like terms, and that puts me to here. All right, and so now I've got like this is dy dx, and this is dy dx. And so we're looking at it, and it's like, all right, well, they're supposed to be equal to each other. So if you just start looking at it, we've got like stuff in front of x, and this guy has 0x. So 1/2 plus m has to be 0. That means m has to be negative 1/2. And then the stuff without x's, well, that doesn't have an x next to it, and that doesn't have an x next to it. So those guys got to be equal. We already know that m is negative 1/2 from the first part, so that's there. And then add your 1, and that puts you to b equals 1/2. Now that part was only worth 2 points. So add a 9. If you missed that completely, not that big a deal.